Here's a video to help with converting between moles and atoms or molecules. Now, if atoms are Legos, molecules would be the little cars or little helicopters that you build when you put them together. And that's one scale. We live on an enormous scale compared to atoms and molecules, a different scale. Every time we exhale, we breathe out more atoms than there are stars in our galaxy. And so when we're making measurements, even of stuff that seems really small to us, like a few drops, that's enormous numbers of atoms and molecules. Numbers that are gigantic and not very intuitive. So instead, we can put them in really big groups and make them a smaller number. Instead of having enormous numbers of atoms or molecules, we just have a few groups that are really big of atoms or molecules. And the name for those groups are moles. So 1 mole of atoms is a group of 6.022 times 10 to the 23rd atoms. So just like one pair of something is 2 of that thing, and a dozen of something is 12 of that thing, a mole of something is 6.022 times 10 to the 23rd of that thing. And it could be atoms, or it could be molecules, it could be anything. You could have a mole of peas. That would be 6.022 times 10 to the 23rd peas. And if you had that many peas, it would cover the entire surface of the Earth, 900 feet deep. If you could have a mole of dollars, and that would be 6.022 times 10 to the 23rd dollars. If I was very generous and I decided to give you a mole of dollars the moment you were born, and you gave away $1 billion every second, and lived to be 80 years old, you would still have more than 2/3 of the money I gave you. So a mole is an enormous group of stuff. But we use it in chemistry to take enormous numbers of molecules we're dealing with and convert them into smaller numbers, more intuitive numbers of moles. So these are going to be conversion problems. A question might say something like, find the number of bismuth atoms in 17.78 moles of bismuth. So that's about a chunk of bismuth the size of a fist. So these are conversion problems, and in all conversion problems you want to recognize first what units are they asking for, and in this case it's the number of bismuth atoms. And second, what number are they giving you? In this case that's 17.78 moles of bismuth. And to do the conversion, you need a conversion factor that relates those two units. How do moles of bismuth relate to atoms of bismuth? We just saw that 1 mole of anything is equal to 6.022 times 10 to the 23rd of that thing. So 1 mole of bismuth atoms is going to be 6.022 times 10 to the 23rd bismuth atoms. Now that we have the conversion factor, we can take the number they gave us, which was 17.78 moles of bismuth, write a multiplication sign, fraction bar. The units we start with go on the bottom of the fraction so that they'll cancel out, and then we can fill that fraction in with our conversion factor. Next to moles of bismuth, we'll go the number 1, going over the fraction bars, like going across the equal sign, and on top, we'll have 6.022 times 10 to the 23rd atoms of bismuth. Moles of bismuth cancel, and we are left with 1.07 times 10 to the 25th atoms of bismuth. And that would be our answer. Now be careful, when you plug these big numbers in a calculator, make sure you put parentheses around them. So you'd have 17.78 times, open parentheses, 6.022 times 10 to the 23rd, close parentheses, then hit enter, then divided by 1, enter, and you should end up with this number. An enormous number of bismuth atoms. Bismuth is an interesting element. When it's exposed to oxygen, it'll get this sort of technicolor patina on the outside of it. That can be kind of beautiful. This is liquid bismuth, oxidizing in real time. Oxidizing means it's reacting with the oxygen in the air, and it's forming that sort of technicolor surface. Alright, what if we wanted to find the number of water molecules in a water bottle, which is around 27.78 moles of water? So first, what units are they asking for? They're asking for water molecules. And second, what number do they give us? They give us 27.78 moles of water. So now that we have identified those two things, we need to find out how those units relate. How do moles of H2O relate to molecules of H2O? And 1 mole is always equal to 6.022 times 10 to the 23rd molecules or atoms. So we have our conversion factor. We can take the number they give us, 27.78 moles of water, write a multiplication sign, fraction bar. The units we start with go on the bottom of the fraction, so they'll cancel out. And then we fill in that fraction with our conversion factor. So next to moles of water, we'll go the number 1. Going over the fraction bar is like going across the equal sign. And on top, we'll have 6.022 times 10 to the 23rd molecules of water. The moles of water cancel out, and we are left with molecules of water. And if you plug this in a calculator, you'd put it in as 27.78 times, open parentheses, 6.022 times 10 to the 23rd, close parentheses, then hit enter, divide it by 1, enter, and you should get 1.673 times 10 to the 25th molecules of H2O. That's how many molecules are in one of those bottles of water that we carry around all the time. Now, to give you a sense of how big of a number of molecules that is, that would be the number of grains of sand that would fit inside of a box that was 240,000 miles on every side. Now, the distance from Miami to New York City is around 1,300 miles. So if you took that distance from Miami to New York City and you multiplied it by 184, that would be one side of this box, a box that was that length, that width, and that height, and then filled it up with sand. The number of sand grains in there would be the same number of molecules of water in a water bottle. Alright, this one asks you to find the moles of carbon in 1 times 10 to the 11th atoms of carbon. That's about how many stars there are in our galaxy, the Milky Way galaxy, 1 times 10 to the 11th. So here, what units are they asking for, and what numbers are they giving us? Well, they're asking us to find the moles of carbon. And the number they're giving us is 1 times 10 to the 11th atoms of carbon. So to do that conversion, we have to know how those units relate. How do atoms of carbon relate to moles of carbon? Well, we know there are 6.022 times 10 to the 23rd atoms in 1 mole. So we have that conversion factor. Now we can take the number they give us, 1 times 10 to the 11th atoms, write a multiplication sign, a fraction bar. The units we start with goes on the bottom of the fraction bar so that they'll cancel out. And then we fill that fraction in with our conversion factor. Next to atoms goes 6.022 times 10 to the 23rd. Going over the fraction bar is like going across the equal sign, and on top we have 1 mole of carbon. So atoms cancels out, and we are left with moles of carbon. And the way you'd plug this in a calculator, you'd have open parentheses, 1 times 10 to the 11th, close parentheses, times 1, enter, divided by, open parentheses, 6.022 times 10 to the 23rd, close parentheses, enter, and you should get 1.66 times 10 to the negative 13th moles of carbon. So you can get a sense of how big a mole is. If all the stars in our galaxy add up to such a small proportion of a mole, that would be a 0 point and then 12 zeros and then 1/66 of a mole of carbon. This question is asking us to find the moles of carbon dioxide in 1 times 10 to the 21st molecules of carbon dioxide. Now, where's that number coming from, 1 times 10 to the 21st? That's about how many stars there are in the observable universe. So the assumption is that we've got 10 billion galaxies, and in every galaxy there's 100 billion stars. So if that's the case, we'd have around 1 times 10 to the 21st stars in the whole universe that we're living in, that we can observe. So if we had that many molecules of carbon dioxide, which we're breathing out right now, how many moles would that be? So first, what units are they asking for? Moles of carbon dioxide. And what number are they giving us? 1 times 10 to the 21st molecules of carbon dioxide. So it's a conversion. In order to do a conversion, we have to know how those two units relate. How do molecules of CO2 relate to moles of CO2? Well, we know that there are 6.022 times 10 to the 23rd molecules in every 1 mole. So we can take the number they give us, 1 times 10 to the 21st molecules of CO2. Write a multiplication sign, fraction bar, units on top go on the bottom, or the units that we start with. The molecules of carbon dioxide go on the bottom of the fraction so that they'll cancel out. Then we're going to fill that fraction in with our conversion factor. So next to molecules of CO2, you'll put 6.022 times 10 to the 23rd, going over the fraction bars like going across the equal sign, and on top you'll have 1 mole of carbon dioxide, CO2. Molecules of CO2 cancel, and we're left with moles of CO2. And if you put this in a calculator, you plug it in like this, open parentheses, then 1 times 10 to the 21st, close parentheses, times 1, then hit enter, divided by, open parentheses, 6.022 times 10 to the 23rd, close parentheses, then hit enter again. You should get 0.00166 moles of carbon dioxide. So if you had as many carbon atoms in the universe, if you had as many carbon dioxide molecules as you have stars in the observable universe, it still wouldn't even make up more than 1,000th or so of a mole. So it's not even a single mole, all the stars in the universe. And that would be your answer. Now, that many molecules at room temperature would take up, that many molecules of carbon dioxide at room temperature would take up around 1.81 milliliters. And you can see here about the size of 1 milliliter. 1.81 milliliters would be around here. Thanks so much for your attention.